everyone, welcome to lecture 25 of Mathematical Modeling and Simulation. In this lecture we are going to talk about Markov chain. If you remember, in the previous lecture we talked about Poisson process, one kind of a stochastic process. So this Markov chain model or process, Markov process which you can say, is another type of stochastic process which we are going to talk about today. So let's first try to understand the meaning of this Markov chain, and then we'll have a look at transition probabilities followed by an example. So what is this Markov chain basically? In 1907, A. Markov began the study of a new type of random process in which the outcome of a given experiment can affect the outcome of next experiment. Such an experiment is called Markov chain. So to understand this definition, let me recall you one of the properties which we discussed in the previous lecture, memoryless property, and that was a property associated with Poisson process. So what was the meaning of this memoryless property? That the outcome, or you can say the number of arrivals, because that's what we count in Poisson process. We always count something. It's a counting process. So the number of arrivals of customers in a bank or in a restaurant in a given interval is independent of the number of customers arriving in that place in any other interval. So that means the states, the independent interval data or output are independent of each other. They do not depend upon anything. So that means if I want to go to the restaurant right now, so my decision is obviously not going to be affected by whether anybody in the city or in the world went to that restaurant in the morning or not. So it's a memoryless process, right? So the number of arrivals are independent of what happened just in the past. But this Markov chain is quite different from that in the sense that it has a connection with the previous step, right? So whatever are you whatever state of the system you are at a certain time, then it is going to affect your next output. So that means there is a dependency on the current state. So it's just one step dependency, that your next result or your whatever are you measuring, so that depends upon your individual experiment to experiment, whatever quantity are you measuring or whatever probability are you finding. So what idea it is saying, that it depends upon the given state, it's not independent of it. So that's the meaning of this Markov chain. So to understand the example of Markov chain, you can have this example of how this COVID-19 situation is spreading, right? So say if you're counting the number of infected and the number of, say, recovered people. So let I denotes the number of infected, R denotes the recovered persons. And say if you want to get a transition from infected state to recovered state, or you are just measuring the data, then the probability of an infected person infecting others, or you can say the number of infected persons increases, will depend upon how many infections are there currently into the system. So that means whatever are you measuring is really dependent on the current data, the given situation. And similarly, how many people are getting recovered will also depend upon how many people are infected, because out of those many infected people, only some people are going to be recovered. So there's a connection which you can understand. That means if I'm going to count the number of infections in a particular city tomorrow, so that really depends upon the number of infections in the city today. It's not independent, because only the infected persons present in the system are going to increase the infection, right? So that's an example of a Markov process. So whatever is connected, and because of this connectedness, it forms a chain. Okay, so suppose initially it was, the system was in some state, whatever it is, it was first state, it affected the output of state 2, it affected state 3, and so on. So there is a chain kind of formation. So this chain is known as Markov chain. So the third state is independent of the first one, but it depends upon the second one. So there is no direct dependency on the previous state, but there is a direct dependency on the given state or the just one previous step, right? So I hope it's clear the distinction between the memoryless property and the Markovian property. These systems are known as having Markovian property. Okay, so we can have plenty of other examples also. So now let's define the mathematical formalism of this kind of chain. So here we have a set of states denoted by SI, I equals to 1 to n. The system moves from one state to another successively. So that's what I just explained, that it does not remain in one system. It's a dynamic process. The system is continuously moving from one state to another in time. So whatever unit of time you consider it 1 day, 1 minute, 1 hour. So that depends upon your observation when the system is undergoing a change from one state to another, but it definitely goes change from one state to another. Each move or each transition, this is called a step. The probability of transition from one state Si to some other state Sj is denoted by Pij. So here we'll have states S1, S2, Sn. Suppose currently your system is in S2 state. So there is some probability that it will go to some other state, right? So that probability is denoted by Pij. So I, that because you are moving from state Si to J, because you are moving towards the state J. So you are moving from ith state to jth state. And this does not matter, as you will see in example. The numerology or the terminology does not matter, means whichever state you can call first, whichever you can call second, that's just a notation. But what matters is the probability of going from one particular state to another state. Like again, I can give you the example of this, say COVID-19, that if a person, say, has been exposed to infection, say exposed, say there is a state, these are the states, say susceptible to infection, the person who is susceptible, then the person who is exposed to infection, that means that has come in contact with an infected person, and then the next state is getting infected and the final state is getting recovered. So if there is always a probability associated here, just like we study in epidemiological models, that there is a rate of transmission from one state to another. So if a person gets exposed to an infected person, so what are the chances that he or she will himself or herself become infected? So there is a chance here, there is a probability here. And similarly, if a person is infected, what are the chances of his or her recovery? So what is the recovery rate? What is the probability of the person to be recovered? Like we know in COVID-19, the recovery rate is quite high. Most of the people are getting recovered. It's only the uh, deceased people who already have some serious illness, they are not getting recovered, but otherwise most of the people are getting recovered. So the probability of getting recovered from the infection is quite high in case of COVID-19, right? So that's an example to understand that whenever system moves from one state to another, it always brings with itself a probability sense. So that probability we should know if you want to understand how the system is behaving dynamically, or what is going to be the long-term effect of this kind of transitions. So when these PIJs are known to us, we form a matrix and call that transition matrix, because you know the notation will be like, because if say there are two states, say I equals to 1, I equals to 2, and j equals to 1, j equals to 2. So it will form a 2 cross 2 matrix, right? You can go from 1 to 1, so it's P11, 1 to 2, P12, P21 and P22. So the probabilities, if you put in the form of an array, that becomes a matrix, that becomes a square matrix, then that matrix we call the transition matrix. And with examples we will see how important role this transition matrix plays in doing the calculations, right? So let's move with this example. This is an example that actually I've taken a screenshot from a book. So you can read this statement from here and we'll understand what is our purpose of considering these kind of examples. What we are trying to figure out in these kind of questions. Right, so this example says, according to Kameny, Snell and Thompson, the land of OZ, so that's basically the name of the country, is blessed by many things but not by good weather. So this is the information coming from for a particular area, geographical area. So there are 3 states possible. The weather is not right there. So they are actually talking about Australia. So that's the short form of OZ, stands for Australia. So the land of OZ is blessed by many things but not by good weather. So they never have two, if we continue the reading this statement, they never have 2 nice days in a row. Nice day means whatever can be their definition of a nice day. Let's not go into the detail, but that's how just they have specified the state of a day. It's a nice day. It's a sunny day. Maybe a sunny day they are calling a nice day. If they have a nice day, they are just as likely to have snow as rain the next day. So that means if you are in a state of being nice, if the day is nice, then there is an equal probability of the system of the day or the weather to be snowy or rainy the next day, right? So there is a half probability of it may rain the next day or it may snow the next day. So that's the probability they are telling you to go from which state to other state. So from nice state, if you go to snow or rain state, so the probability is equal. If they have snow or rain, they have an even chance of having the same next day. So that means if you are having currently, if today it's snowy, so there is an even chance of having same next day. So it will be snowy tomorrow as well. They have an even chance. It means snow can go to rain, rain can go to snow with the equal probability, right? So that's the meaning of the even chance. And if there is a change from snow or rain, only half of the time it is changed to a nice day. So that means, see, half of the time it changes the state, like snow to snow is equally likely as snow to rain. That was the meaning of this term, this line. Now this sentence is saying if it is changing from snow or rain, then half of the time it is going to change to a nice day. So half probability go from snow to nice and rest has an equal chance. With this information, we form a Markov chain as follows. So we have 3 states: rain, nice, snow. From the above information, we determine the transition probabilities and represented in the form of a matrix. So in most of the questions, we are given the transition matrix, but even if it is not given, then the first thing we need to do in these questions, we need to learn how to formulate the transition matrix. So here I've just read the statement and now we can interpret the meaning of the statement in the form of probabilities. So the first line, if you start reading from here, they never have 2 nice days in a row. So that means the probability of going from. So actually this transition matrix is representing from, it's a one state jump, like from today, what is going to be the state of the weather tomorrow, right? So today there are 3 possibilities. It is either rainy, nice or snowy. So tomorrow also there are 3 possibilities because other than these 3 states, no else weather state has been defined. Now we just need to know their individual probabilities. What is the probability from R to R, R to N, R to S? N to R, N to N, N to S, and S to R, S to N, and S to S. So that will be 9 probabilities we need to determine, right? So this entry is actually denoting R to R. This is R to N, and this probability is R to S. But now let's come to how they have computed these probabilities. Okay, so this line I was explaining, they never have 2 nice days in a row. That means the probability of going from nice to nice is 0. they never have this happening. So that means n to n. So here it is definitely written 0. If they have a nice day, they are just as likely to have snow as rain the next day. So obviously if they are having a nice day, that means you are at this state, so it's equally likely to rain or snow. So equally likely means because this is 0, so obviously it has to be half half. See, one thing should be clear, that from whichever state, say you are going from rainy state today, and tomorrow there will be exactly one state possible, either rainy or nice or snowy. But the sum of these probabilities should be equal to 1. Why that should be 1? Because at least, because exactly one of that is definitely going to happen. So the probabilities, the sum of probabilities of R2R, R2N and R2S has to be equal to 1. So same is true for the other rows also. So that's a property of transition matrix. You can say that the sum of the elements of the probabilities, sum of the probabilities which you have written in a row should be equal to 1. So this information is helping me to decide that if this number is 0 and these are equally likely of each other, so the only possibility they can be half and half. So that's why this is 1 by 2 and 1 by 2, right? And now you just continue the statement and get the other values. So if they have snow or rain, so that means if they are here or they are here, then they have an even chance of having the same next day. Same next day means snow to snow or rain to rain. So snow to snow means this number and rain to rain means this number. So there is an even chance. Even chance means it's equally probable. So therefore its a probability is half and half. There's an even chance of doing that. So whenever they're talking about even chance, so that means it's half probability. They are talking about 1 by 2. If there is a change from snow or rain, only half of the time this is a change to a nice day. So if rain is going to change to, because rain to rain we know now it's 1 by 2. So that means the sum of the probabilities from R to N and R to S is going to be 1 by 2, because the total has to be equal to 1. And so since there is a half of the time it is changing to a nice day, so half of 1 by 2 is going to be 1 by 4. So it obviously means the other one is also 1 by 4, right? So I'm just reading the words and interpreting the information in the form of this matrix. So, and similarly, from snow to rain or snow to nice, half of the time it's changed, so it's 1 by 4 and the remaining 1 by 4 is written here. So we have formulated the transition probability matrix, and now we need to discuss why we are doing so. What is the need of computing this transition probability matrix? So we are asked a question here, that if it is snowy today, then what is the probability that it will be rainy 2 days from now? So these kind of questions are asked, that you are given that system is in, say, one particular state today, what is going to happen after 2 days? In what state it will be, or what is the probability of the system to be in that particular state after 1 day or 2 day or whatever. So they'll give you a timeline and you have to find the probability. So this is a question asked for this example, that if it is snowy today, if it is snowy today means you are here, what is the probability it will be rainy 2 days from now? So you want to actually go from S to R. So from snowy, you want to go to rainy after 2 days. Means in 2 days you want to get over here. So S to R, but you want to go through 2 days. So there will be 2 steps involved. Firstly, you have equal probability of going from R to N to S. You have 3 possibilities, that from snowy, like, okay, so this is today, this is tomorrow, the next day, and this is after 2 days, the day after tomorrow. So we have to reach here. So in between the next day, there are 3 possibilities. We do have an answer for today, it is snowy. We do have an answer for the day after tomorrow, it should be rainy. But the intermediate 1 day can have any of the 3 states possible. So we have to have the 3 possibilities for there. And now we will look at the individual probabilities. So from S to R, the probability is P31. From S to M, the probability is P32. From S to S, the probability is P33. R to R, the probability is P11. I'm just reading from here. R to R, this is P11. N to R, so this is N to R, this is P21. And S to R, this is P31. So we want to go from S to R in 2 days. So obviously the answer is going to be, the required probability is going to be computed by this formula. So required probability is equal to P31 into P11 plus P32 multiplied with 21 plus P33 into P31. So if you substitute their values from the matrix, so you can read the values of these individual probabilities from the matrix and you will get the final answer is 3/8. So it's easy to understand why this is the required probability, because see, you want to go from S to R and either of this way will be adopted. Either you will go from S to R, or you will go from S to N to R, or you will go from S to R. So since there is a or involved there, so there is a plus sign here, but here these are independent. Like these should be multiplied, because if you want to go from S to R, so the probabilities of this happening and this happening should be multiplied with each other, right? So it should be P31 into P11, and similarly for the other steps. So the overall it gets added up and you'll get the final answer is 3/8. So we got an answer to our question that if it is snowy today, what is the probability it will rain after 2 days? So the chances are 3/8. That's the probability. Similarly, you can ask any kind of questions in this. Everything will be answered just in a similar manner with the help of using this transition matrix. You just need to know the values of the probabilities. So now I'll tell you alternate technique of computing this. If you do not want to use this formula of multiplication of the probabilities, so we'll use an alternative technique to do that. So I'm explaining that alternatively, we can solve this problem as follows. So we'll compute p square and then in the matrix p square we find the value of entry S to R, which is 3,1. Why it is 3,1? Because you see S to R is this SR. So this entry is 3,1. That means in terms of numbers, you can say you are moving from third stage to first stage. So I have to read the entry 3,1 in the matrix P square. So now the question arises, why P square? Why P square? Because the statement of the question demanded that what is going to happen after 2 days. So because of that 2, it's a square here. If the same question would have been what would be happening after 3 days, so I would have done P cube here, because one time usage of matrix P means that is giving you a transition from one time step to the next time step. It's a one time step. So if your unit of time is a day, so that means one time consideration of probability transition matrix is giving you towards the state of tomorrow. If you want to get 2 days advance, so it has to be p square, p into p, and then again p into p into p. You'll get the information for the 3 days, after 3 days. So this p square is done because I was asked what is going to happen after 2 days. Okay, so that's why. So now let's just compute p square. So these are the values I'm getting. So that's just a squaring of the matrix, nothing hard in that. And in this matrix, I need to know this 3,1 entry, which is 0.375, which is 3 by 8. And 3 by 8 is calculated earlier, because with the previous technique which I just explained you, that was giving us the value probability 3 by 8. So this way also we are getting the answer 3 by 8.375. So this is the better way of doing the things, because here you do not have to do any individual diagram formation and then computing the exact expression of which probability to be multiplied with which probability and added in which other probabilities multiplication. So no need to do those kind of calculations. This is a better way, because here we just do the raised to the power of the transition matrix by that much time step, whichever is asked in the question, and then we find that particular state change entry into that matrix. Okay, so that's the answer we are getting using this technique also. So now we have another kind of question. Suppose we are given that the system initially has a probability distribution of its states. For example, if it can rain, ice or snow, then the probability of each of three states is given. So just unlike the previous example which we just discussed, there the information given was that it is snowy today. So they were telling you the information for today, the current state, with 100% precision. Like they were telling you it's snowy today, so that means the probability of being rainy or being nice today automatically becomes 0. But this time I'm going to take the question when they do not even tell you what is the current state. Rather they give you a sense of, they give you a value of the probabilities of the system to be in any of the states today. That means at the current time. So this is what I was talking about. So say u 1 by 3, 1 by 3, 1 by 3 be the initial probability vector for the system. Then to know the probability distribution of states after say 3 days is computed as up cube. So the vector you have to multiply with p cube. So this is the p cube I have computed, and multiply with the unit with the u vector, you will get this as your answer. So this is another kind of question which you can answer with the help of transition matrix, that instead of giving you exact state on one particular day, like in the previous case we were having snowy today and 2 days after it is going to rain, so the initial and final state were fixed. But here in this question we do not have any fixed state, rather they are talking all in terms of probability, that if this is a probability vector today, like what is the interpretation of this vector I can explain. This says that there is a 1 by 3 chance of the day or the weather to be rainy today, 1 by 3 chance of it to be nice, and 1 by 3 chance of it to be snowy today. Then what is the probability distribution? What are these values will change to some other values after 3 days. So we are actually finding a change in the probability distribution. So we need to multiply this with p cube, because they are asking after 3 days, right? So just multiply this u vector with p cube and you will get this. So that means after 3 days, these will be the values of the probability. So after 3 days, that means on the 4th day, there will be 0.401 probability of rain, 0.188 probability of the weather to be nice, and 0.401 probability for the weather to be snowy. So that's the another kind of calculation which you can do. So that's all about Markov chain models. More of it we will learn in lab, how to do the simulation of these Markov chain. So that part we will learn in lab. And in the next lecture, we are going to focus on introduction to financial mathematics.